Geometry lesson 5-1. Spent some time talking about triangles. There's quite a few different situations involving buildings that have had some amazing architecture involved. This is looking at a building from down below upward at some of the windows that are in, and you can see how they stick out in kind of a funky way, that's for sure. But there's definitely some uniformity to it and how it flows. In this particular shape, you can see that the buildings do not seem to have any kind of symmetry whatsoever, but they are very large shapes. They're very attractive in the terms of like they look aesthetically pleasing. They're different yet unique, so it's kind of a fun building. And this one a little bit more in relative just flat sides, but you can see you've got a trapezoid up here and maybe forming a triangle in the middle. You know, it stands out. I think that's one of the greatest things about architecture and geometry is that it really allows itself some kind of creativity that's involved. Here you have some different shapes. It looks like these are stacked up boxes, when in actuality they're built that way. They're very stable. It looks like they could topple at any moment. But you see some sort of flowing, geometry to each one of these shapes. I think that's kind of one of the neatest things about geometry is where it could take architects. Just lends itself so great to that. So here we have what we call perpendicular bisectors, and I know you're like, what did that have to do with all those pictures? Well, in those pictures you have lines that are perpendicular to each other. They take place quite a bit. So perpendicular bisectors can be segments, they can be rays, they can be lines, they can be a plane. Any of those that are actually perpendicular to a segment at the very middle. So without bisector, if I just said they were perpendicular in general, they could cross it at any point and be 90 degrees. But in order for them to be a perpendicular bisector, it has to be crossing at the middle. Right? So it's going to cross that segment at its middle. Why would we say that it's not perpendicular to a line? Because a line is going on for both directions forever. There is no real middle. Anywhere is the middle since it goes forever in both directions. Right? Equidistant, equa meaning like equal, and distant for distance. They're going to have the same distance apart, equidistant. Now, the perpendicular bisector theorem states that if a point is on a perpendicular bisector, it's actually on the bisecting portion that's crossing a segment itself, then it will be equidistant, the same distance, from the endpoints. So this is a diagram of that. Let's say the green line right here is the segment that's being bisected. That means that this line right here, this distance here and here, would be exactly the same because it's bisected. It's perpendicular, meaning that's 90 degrees. And according to the perpendicular bisector theorem, the distance from here to here would be exactly the same as from here to here. They would have to be the same. There's no way about it. The only way that could change would be if you had the line like this, and the line was coming through, and then this line would be shorter than that line, but this would not be 90 degrees. That's the only way that you could change those. So they would have to be the same value. All right? The converse of this. Now, if a point is equidistant to the two endpoints, if you know that this distance and this distance are the same, you're pretty much forcing this point to be on the perpendicular bisector. So remember, they go both ways. If you know you have a perpendicular bisector, then you know that it's the same distance from the edges, from the endpoints of this segment. If you know you're the same distance from a point, then you know you're on the perpendicular bisector. It just depends on where you're going. Converse is the same, it's just in reverse order. Alright, the distance from a point to a line. This is a tricky one. People make mistakes with this. The length of a perpendicular segment from the point to the line. What I mean by this, and this is where people make mistakes, say I have this red line and I have this blue dot. Some people are going to measure the distance from here to here and say that's how far away it is. Somebody else might measure from here to here and say that's how far away. So someone might go from here to here and say that's how far away. In other words, if we didn't have a rule like this, we could measure from that point to anywhere and say that was the distance. I think you'd all agree that this green line right here is much longer in appearance than this one. So that doesn't have any kind of uniformity, which is why we have this rule that states the only way we actually measure the distance is if the distance is coming in at 90 degrees. Big mistake there. People forget that kind of info all the time. Where it comes in at 90 degrees tells you where you should be drawing your line to measure the distance. Don't measure over here because it's not coming in at 90. It has to come in and be perpendicular. That's really, really key in order to get that right. All right? The only one that works is the dashed line. The green lines will not work for the distance from the point to the line. You cannot use any of these other green lines as the measurement for the distance. They are not coming in at 90 degrees. No matter where it is, you've got to come at 90 degrees. Now, to be equidistant from the two lines, again, we're talking distance, which means we're going to be talking about 90-degree angles where they come in. When a point is the same distance from two different lines, we're talking about this. You'll notice I put 90 degrees here and 90 degrees here. I am not saying that this distance equals this distance, because this would not be 90. It has to be where it comes in at 90 to be the same. So if somebody saw a diagram that looked like this, and there was a dot here, and someone said, well, that distance is the same as that distance, that does not mean they're equidistant, because that's not 90, and that's not 90. They have to be coming in at perpendicular angles. Be very careful about that. That's one of the biggest pieces right there. And our last bit of information, angle bisector theorem. If a point is on an angle bisector, remember what an angle bisector is, it's bisecting, cutting it into two parts, then it is going to be equidistant from the two sides. So in this case, the red is the angle, the purple line represents the angle bisector, right? And to be on that angle bisector means it will be coming in at the same distance away. It doesn't matter even where. Right here, that's 90, that's 90. These two would be the same distance apart. Or up here, 90, 90. Those would be the same distance apart. It doesn't matter where you are on that perpendicular bisector, or on that angle bisector. Anywhere on that angle bisector is going to be the same distance from the angle itself, the two sides of the angle. And to flip that around, if you know you're the same distance, then you know you're on the angle bisector. So if you're stating that you're on the angle bisector, that means you're the same distance from the sides. And if you know you're the same distance from the sides, then you know you're on the angle bisector. Converse of each other.